So hello friends, welcome to all of you. So this tutorial we are going to learn about how meshing works in OpenFOAM. Okay. So for this purpose I have created one test case and one solver, that is the understanding the mesh. Okay. So if I show you steps of creating this solver, so you remember from last class we are following the same procedure. Okay. So I have just created the app using the foam new app, and the solver name is understanding the mesh. Okay, so with this I have created the solver, and after this I am compiling to check that whether this everything is fine with the solver or not. Okay, now I have added few lines from my side. So if you remember, I told you that Fscmt is the basic header file that you always required if you want to create any new solver in OpenFOAM. Okay, now after this you always find that there is one setRootCase.H folder. Okay, so if you open the setRootCase.H, okay, then you will find this is the same line. It is written here in the setRootCase.H. Okay, so what this header file does, it always check that whether the file structure is same as or not. Okay, so if you are going to compile this solver on this test case, so it is going to check that whether these two folders are present or not, constant folder and system folder is present or not. This is going to check here using, if we are using the setRootCase.H. Then after that we are creating the object of time. Okay, so you can see there, this is the form, that is the namespace we are using, and then after that we are calling the time class, and we are creating one object of the time class, that is the runtime. Okay, and so this is the one way of constructing the time class. Okay, so this is the constructor of time class. So these two things, this one and these things, both have the same meaning. Okay, now after that we are printing one function of the, so this is the object we have created of the time class. Now this object has many functionality. Out of this functionality we are calling the time name. Okay, so this is the object of time class. Now this object has the many functionality. Out of this those functionality we are calling the time name, that will print the current time name. Okay, now this is the createMesh.H, create the object of the mesh. Okay, so same thing we are writing here. Okay, so this is the same thing, createMesh.H is the same thing written in the createMesh.H. So if you search it on Google, you will find the same thing. Okay, so you can see here that this is the same thing. Okay, it is creating one object of FB mesh. Okay, name as the mesh. Okay, so what does it mean? So this is the foam FB mesh, that is the class. Now we are creating a mesh as a object. Okay, now this mesh object has different functionality, that is the cell size. Interface means if you want to read the faces, that will give the face size, and if you want to read the cell center of ith cell, that is this functionality. So let me give you one example. So here I am giving one example. So I have taken this to test case from the last class. If you remember, we have created the block type of geometry using the block masjid. So from there I am taking this test case. Now if you go there, so this is the block we have created, and we are just putting one cell in each direction. Okay, so in XYZ we are putting only one cell. We have 6, and I am opening the paraform block. So let me open the block of this mesh, then it will be clear to you. Okay, so this is the block. Okay, so this is the block, this is the 0 1 2 3 and 4 5 6 7. Okay, so we are specifying only one cell in each direction. So in X direction this is the cell size. Okay, so whatever the length of this is, that will be the cell size. In a Y direction this is the cell size, in Z direction this is the cell size. Okay, so we are just creating this whole block as a single cell, and let's explore everything about this block or this cell, and it will apply to any kind of cells. So let me first run here block mesh. So mesh has been created. Now if I print check mesh, okay, you can see here that total number of points is equal to 8. Okay, so total number of point will be 8. So 1 2 3 4 5 6 7 8. Okay, so these are the points, and if you see the faces, so total faces will be 6. This number, these are the faces of these cells. Okay, and this is the hexahedral meshes, because there is a cube type of mesh is called the hexahedral meshes. So if you check the number of cells, so number of cells equal to 1, because we are just creating this as a one cell. So this is the everything is shown here. Okay, now if you go to the constant folder, so there is a one folder that is the polymesh, that is everything about the meshing. Everything tells here about the meshings. Okay, now if you go to the points, so whatever points we have created, okay, so this is the same points we have created during the block mesh. So these are the points. So these things you remember, we are using the mm. Okay, so millimeter we are considering the meters. Now this every one will be converted into the millimeter. Now you can see that these all the points will be mentioned in the point section. Okay, so this is the one points, this is the second point, this is the 4 points, this is this, these are all the points. Okay, so this will be written in the points of the polymesh. Okay, now remember 4 points will meet and will made a one face. Okay, so you can see here that these are the faces where 4 points are matching each other and creating one face. Okay, so here this one 1 2 3 0 1 2 3 4 5 6 7. Okay, so you can see here that from these points we are creating one face, then the second face, so total there will be 6 faces. Okay, now let's run the solver we have created here. Okay, so this is the solver we have created here, and let me run this solver, and then we are going to again access all these things for this tutorial. Okay, so we are going to also access this cell size, face size, sorry, this should be face, then cell center, and other functionality we are going to explore in more detail. Okay, so let me first compile the solver here. This, now if I run this solver, okay, so see, we are just printing the time. Currently we are not printing anything other than time, so that's why it is printing that current time is the 0. Let me first write here mesh size. So this thing I am copying here. So it will print how much cells the meshing has. It is going to print here. This will print the face size. Okay, so how much, what number of faces is there, that is going to print here. Okay, so let me again compile it and then run the solver here. So again if I run the, you can see here that it is printing that it has one cells and it has 0 faces. Okay, now you are 0 internal faces, so it should be here that it has the 0 internal faces. Okay, so if I again run here, I have 0 internal faces. Okay, because there is only one cell, so it has no any internal faces other than boundary patches. Okay, remember this mesh.cf.size will not print the boundary patches, so there should be other than boundary patches, then it will show the how much internal faces are there. Okay, so for that purpose let me just create another test case. Okay, now let me increase the number of cells in each direction. Okay, number of cells in each direction. So when we increase the number of cells in each direction, in x direction there will be 2 cells, in y direction there will be 2 cells, and in z direction there will be 2 cells. Okay, so there will be a total 8 number of cells. Okay, it should be, there should be 8 number of cells. Just find out how much faces will be there. Okay, now if I run the check mesh. Okay, so now you can see here that there is 8 number of hexaedrals. So there will be 8 number of cells, and there will total how much points? So total there will be 27 points. Okay, and internal faces, earlier there was 0 internal faces, now there is a 12 internal faces, and total number of faces is 36. So out of this 36 there is a 12 internal faces, and other faces are the boundary faces. Okay, so let me run the solver here. Okay, so then we can see here that there is a 12 internal faces and mesh has total 8 cells. Now let me see it in the paraform. So if you open the paraform and surface with page, so you can see here that there is 1 2 3 4 5 6 6 7 8. Okay, so total 8 number of cells are there. And now you can count the total number of boundary patches, boundary faces. 24 faces are boundary patches. So out of 36, so what I was saying that there is 20 total 36 faces are there, out of which there is 24 faces on the boundary. So there is 24 faces on the boundary. You can see here easily, you can recognize here. So 36 minus 24, there is total 12 faces. So these faces are the internal faces. So if I cut here from center, so these are the internal faces. Okay, so these are the internal faces. So 1 2 3 4. Similarly there will be in x in y direction. So 1 2 3 4, and similarly there will be in z direction 1 2 3 4. 4 plus 4 plus 4 is equal to 12 faces are the internal faces, and rest 24 faces are the boundary patches. So that is what it is showing here. It has 12 faces internal face, and total face is 36. So 36 minus 12 is equal to 24, and you can see here that there is 8 cells, and rest you can total 8 number of cells. Now if you go to the this polymesh sections, so you can see here that there will be total 27 points. 1 2, these are the points. Okay, so these are the points of the cells. Okay, okay, so these are the points. So you can see here that 1 2 3 4 5 6. Okay, so 3 3 3. Okay, total 9 points are these sides. Okay, now similarly you can count in every direction. So there will be overall 27 points. This is what it is showing in point folder. And now these points will create the, this points is going to create the faces. Okay, so you can remember, you can see here that 4 points creating one face, 4 points creating another face, 4 points creating another face. So there will be total 36 faces are there. Now what is the neighbor and owner? Okay, so every internal face has 2 cells which are attached to it. Okay, so so if we talk about this face, what I mean to say that, so if we talk about the this internal face, okay, so this red internal face has total 4 internal faces. Okay, so this one is the 1 2, similarly here 3 and 4. So this red has 4 internal faces, and each face has 2 cells, one on the left side and one on the right side. So here also you can see here that one on the left side and one on the right side. Similarly, if we talk about this face, so this has also four internal faces. This red box has four internal faces, and each internal faces has uh, two cells. One is the left side and one is the right side. One is the left side and one is the right side. Similarly, if we talk about the this this box has also four faces, and these four faces are the internal faces, and these faces has the one internal one cell this side and one cell this side, one cell this side. So you can see here that every internal faces has two cells attached to it. Okay, so the cells which has lower index, okay, so out of these two cells, the cells which has lower index, that is called as owner, and the cells which has the higher index, that is called as the neighbor. Okay, so this is the concept of the neighbor and owner. Every internal faces have one owner cells and one neighbor cells. Now if you talk about the boundary patches, so you can see here that this boundary patches, this have only one cells. Okay, so this has this by default this patch cells, that is called as owner cells. Okay, so there is no any neighbor cells for the boundary patches. Okay, because every boundary patches has only one cells adjacent to boundary patches. Okay, so by default we called in OpenFOAM that is the owner cells for the boundary patches. Okay, so by this logic there should be 12 neighbor cells. Okay, because every internal faces have one neighbor cells and one owner cells. By this logic there should be 12 neighbor cells, but since the boundary patches have also owner cells, so there should be total 36 owner cells. Okay, so if you open this constant folder and this files, so you can see here that there are 12 neighbor cells. Okay, because every internal faces have one neighbor cells. Okay, so the cells which have lower index, that is called as neighbor cells. Okay, but since boundary patches have only owner cells, that is why you can see here that there is a 36 owner cells. Okay, so this boundary patches have only owner cells, so there are total 24 boundary patches and 12 internal patches. Okay, so internal patches have also owner cells plus neighbor cells, but boundary patches have only owner cells. Okay, now let's explore everything about the meshing. So these are the functions I have written here that you can get knowledge about the meshes. Okay, so using this all the tools of mesh object, you can either use any calculation equation on the mesh cells, or you can access some information about the mesh cells. Okay, so let's explore everything one by one. Okay, so these things we have learned already. So by using this mesh.C.H, you can access the number of cells, and this is the number of faces. Okay, so remember this can be only used to access the internal faces. Okay, now let's open this box and see what it is showing. So here you can see here that you can also access this will give me the coordinates of the every cells. Okay, so this is the mesh.C.I. This is going to give me the coordinates of every cells, and if you want to just access the x coordinates or y coordinates or z coordinates, this information can be accessed by this logic. Okay, now you can also do the similar thing for the faces also. Okay, so same logic I can do for the face also. mesh.cf.size. Okay, so this is going to iterate over all the faces of the mesh. Okay, however there is another technique to loop over
all the faces, that is the for all loop over the all the faces of the mesh. Okay, so I can do here that for all mesh.cf, and I am iterating this I command. Okay, so these two things are equivalent. Okay, so either I can write like this or I can write like this. Okay, so let me just copy from here and paste here. Okay, so I can write face I with center at face.cf.I. okay, so you can also access the x and y coordinates of the face here. Let me just read the x coordinate here. Okay, similarly you can read the y coordinates of the faces also. So I can write here face I x coordinates face mesh.cf.I x is equal to, okay, and I let me just turn off everything. So let me run here. Okay, so let me run here. Now if I run here, so you can see here that first we have run iterate over the all the cells, and for every cells it is giving the center coordinates, and also separately you can access the x and y and z coordinates. Similarly I am running over all the faces, and it is giving the center coordinates of the faces, and you can separately access the x, y and z coordinates. So this is the logic of accessing over the x, y and z coordinates. Okay, now let me just turn off these things. So remember, these two for loop are the similar. Okay, either you can use kind of this, or you can use this thing. This utility mesh.neighbor.size and this mesh.owner.size, this always give the neighbor and owner size of the internal faces. Okay, so it does not tell about the boundary faces. Okay, so it always give access to the internal faces. Okay, so if we are going to run here this size command, it is going me to show the only 12 faces. If I run this command wmake, so it is going to give me this mesh neighbor size is 12 and mesh owner size is 12. Okay, so for internal face 0, this is the cell center of the internal face, and having the owner cell 0 and neighbor is equal to 1. Now if we talk about the face 1, it has the center this, and the owner cell is 0 and neighbor cell is 2. Okay, similarly we have printed the information about the all faces, about the owner cells and about the neighbor cells. Okay, so this way we can access to the neighbor cells and the owner cells. Now if we want to know about information about the boundary patches, okay, so this is the utility you can access using the boundary patches. Okay, so this, remember I have told you about the for all loop. So this is telling about the loop over the all the boundary mesh. So here what we are accessing, we are accessing the patch I. Okay, so this is this boundary patches is start from the first patch, and this will print this will give the index of the patch, every patch, and this will give the name of the every patch. Okay, so what is it is going to read? It is going to read this information. So there are boundary, there is folder name with boundary, so it is going to read this information. Okay, so here are these are the indexes. This is the 0 index, 1 index, 2 index, 3, 4, 5. So there are 5 indexes are there. So this patch I will going to give the index name. Now this is going to read the name of every patch. Okay, so this is the name min x, min y, and min z. This is going to read by this command. Okay, now this is going to give the faces, how many faces this patch has. Okay, so what it is going to read, it is going to read the this line. This is the number of faces, this is the number of faces. So this is going to it is going to read by this command. Okay, now it is going to read the give the start. Okay, so where it is starting. So what does it mean? So when you open this patches folder, so it is there are total 36 faces. Okay, generally the below one are the boundary patches. Okay, so here you can see that start faces is 12. Okay, so if you count from here 0 1 2 3 4 5 6, so from 12 to 4 faces. So suppose this is the 12 number faces, this is the 12 face. So from this 12 faces, 4 faces are given to the min x patch. This is what does it mean. So it is start from the 12 number face, and total 4 faces are corresponding to the this boundary wall. Okay, similarly this will start from the 4 face, this will start from the 16 face, and from 16 to 4 faces it is corresponding to the max x. And similarly this you can see here that 12 4 16 4 20 24 24 24 plus 4 28, and 28 plus 4 32. Okay, so this is what it is showing here. Okay, now if I compile the command, okay, so you can see here that it is accessing the patch 0 index, patch 1 index, and the name is also showing, and the number of faces, which is just these values, number of faces, and also the start total face from where it is starting. So this is the command it is reading here. Okay, number of faces and total start face. Okay. So let me just turn off this also. Functions, there is two important value inside the OpenFOAM. So generally if you are applying the boundary conditions, then this information like normal vector and the surface area of the patch, this is very important function inside the OpenFOAM. Okay, so this is used to apply the boundary condition, kind of like heat transfer boundary condition you want to apply here. So then this normal vector, and this is the surface area. Okay, so again I am iterating over all the boundary patches. Okay, so this is the mesh boundary mesh, and this is the patch ID, and we are again printing the its face number. So see every, in our case every face has total 4 faces. Okay, so every boundary patches has 4 faces. Okay, what I mean to say that, so if you remember, if you open this, so every boundary patches has number of 4 faces. So different test case have different number of faces, but in our case every boundary faces has 4 faces. Okay, so that's why we are only printing the information of the 0 faces. So out of these 4 faces we are only printing the information with index 0. Okay, you can print with index 1 or 2 or 3. Okay, so here the value can be 1, 2 or 3. If greater than 3, then it is going to show the error. Okay, so patch face size is equal to 0, and which is adjacent to the cell, so it will showing to the adjacent cell nearer to the patch face size. So remember, every boundary patches have only one adjacent cell, that is called as owner. So it is going to show the only the adjacent cell. Okay, so that is the nearer to the this boundary faces. Okay, now if you want to access the normal vector, so this is the function which will give the normal vector to the your face, and this is going to give the magnitude of the normal vector. Okay, So this is the very important utilities if you want to apply any boundary kind of condition patches, different patches, then this is the important functionality. And let me show the result here. So you can see here that patch has 0 phase, so it is always reading the 0 phase. Okay, so remember every patch has 4 phases, so out of these 4 phases we are accessing only 0 phase, and all the normal vector and phase area you can access like this here. Okay, and it is showing the adjacent cell. Okay, so every patches has one adjacent cell, and this is giving the information about the every adjacent cell. Okay, now you can logically apply that. If you can access the index of the this adjacent cell, then you can access the any information about the adjacent. This is the way of accessing the faces, all the faces of your mesh. Okay, now this mesh boundary, these things I am storing into the one variable, that is the boundary mesh. Okay, whose type is the poly boundary mesh. Okay, so I am accessing all the mesh boundary information into this variable. Okay, so whatever formula or calculation if you want to apply on the faces, this is the way of doing it. Here we are storing all the faces information, and here we are storing all the mesh boundary information. Okay, now we will iterate over all the faces. Okay. So remember earlier I told you that this for all loop iterate over all the faces here. Okay, so this for all can be used to iterate over the all faces. Okay, now it will check that whether the mesh face is the internal face, and if it is the internal face, then you can apply your calculation here. Okay, so for example, suppose you have declared some u kind of variable, that is the vector quantity, and using that vector variable you are applying that vector 0 will be applied to that u face. Okay, so this is the one way of doing it. Okay, now if this is not the internal face, then of course it will be the boundary face. Okay, so similarly we are saying that if this is not going to this if condition, then it will go to the else condition. Okay, now whatever formula you want to apply, you can apply onto the boundary field also. Okay, so this is the one way of accessing the boundary faces or internal faces. Okay, now there can be another method that can be used to access over the boundary patches like this. So remember we have stored all the mesh boundary information into the one variable, that is the boundary mesh. So again we will iterate over all the boundary meshes. Okay, now we can also access to the what is the patch name. Similarly we can also access like this here, and you can access to any information like the faces or the start phase. Okay, this everything information you can access, and this is the way of iterating over all the faces of the given patch. Okay, so this is the print, this is the one way of doing. So I can print here anything, and if you want to apply any calculation formula, you can patch and let me print the patch name here. So it will print the patch name, and let me print the face ID. So it is going to print all the patch names and all the faces related to that patch. Okay, so if you can access to the patch name and face number or face ID, or so you can access face center also, you can access the adjacent cell to the face also. So any information you can access like that, and you can apply any type of boundary condition. Like you can see here that we are applying one boundary condition to the u field. Okay, and we are specifying that the boundary face have the vector equal to 0 value. Okay, this is the way of iterating over all the mesh points of the boundary mesh. Okay, and let me run it, then the concept will be more clearer. Okay, so there are some use, this is the warning that we are some variable we are just specifying but we are not using it. Okay, if I run here, so you can see here that, let me open it first. So you can see here that this is the patch name, it is showing min-x, and min-x has 4 faces. Okay, so it is showing the 4 faces, and then again max x has 4 faces, min y has 4 faces, and similarly max z has the 4 faces. Okay, so this is the printing the all information of the patch name and the size. Okay, sometimes it is happens that you want to access only some specific patch. Okay, so for example, this way you can access directly the given patch. Okay, suppose I want to access the patch name equal to max z. Okay, so I will just create one word. So it is the word is the one variable, and I am creating one variable with a kind of in a word type, that is the patch name, and in the patch name I am giving the value equal to max z. Okay, now I will going to find patch id. Okay, so this max z id will be find by this function, and the index will be stored into the this value. Okay, so earlier this was the 0 value, but when it is find out by this function, then it is going to store in this value. Okay, now when I am able to find the index of the patch id, then we are going to apply any kind of boundary condition or any type of calculation to the this just specific one boundary patch. Okay, so let me run it here. So okay, so here you can see here that the max z had index 5. Okay, so this is the printing that max z, patch name is the max z, and the index is the 5. Okay, so if I open the this boundary folder, so you can see here that this one the 0 index, 1 2 3 4, and this has the 5 index. Okay, sometime it is required to access the mesh volume. Okay, so it is important to access the volume of each cell of a given mesh. Okay, so here we are going to access the mesh volume of the each cell. Okay, so if I show you this the paraform of this meshing, so you can see that by default in OpenFOAM the mesh are the 3D geometry. Okay, so this is the one kind of cuboid, this is also a one kind of cuboid. So by default mesh construction inside the OpenFOAM is a 3D mesh. Okay, so each mesh has some volume. So if you want to access the volume of the each cells, so this method is going to useful for you, the cell and total volume of the mesh. Okay, so these two things how you can access here. Okay, so I will take one quantity that is a scalar, and suppose sum equal to 0. Okay, now for all, that is the for all loop, and we are going to apply to the all cells of the mesh. Okay, and suppose this is the index I, it is iterate over all the cells of the given mesh. Okay, now I am going to print info for cell number, cell index, and this is I, and we are going to print as volume equal to mesh. This is the v command. V is the going to give me the volume of each cell, and there should be index I, that is the number of the cell. Okay, and this is the indel. Okay, so this is going to print the volume of the each cells. Now we want to add the all the volume. So sum equal to sum plus mesh dot v into I. Okay, now here we can print info the total volume of the mesh is okay, so it is going to print the total volume of cell. Okay, so this will be equal to sum. Okay, now let me compile this solver. So it has been compiled. Now we can run it on our test case. Okay, so you can see here that 0 cell has this much value, 1 cell has this much value, 2 has this much value, and 7 has this much value. Okay, and the total volume of the cell will be sum of the all these quantities. Okay, so this is equal to 1 e to the power minus 9. Okay, okay, here we can also do so cd 3d. Okay, now here you can also run the, so here we have only one cells, and see this 0 cells has the same value which has the volume of the total mesh. Okay, because there is only one cell and that is the block of the mesh. Okay, so this is the all I want to tell you about the meshing. I think this meshing concept will be understood by you. Okay, now please go through all this structure and do it by yourself, and if you have any confusion or any question, you can ask me in the comment box. And please kindly share these videos and kindly subscribe my YouTube channel. So thank you all of you for watching this video.